All right, today we're doing a rapid-fire review of chemical thermodynamics. Have you ever wondered why some reactions just happen all on their own while others need a major push? Well, if that's ever crossed your mind, you are in exactly the right place. I mean, think about it for a second. An iron ship, it rusts. An ice cube in a warm room, it melts. These things just happen. But have you ever seen a rusty shipwreck magically turn back into shiny new metal? Or a puddle of water just decide to freeze itself in that same warm room? No way, right? It's a one-way street, and that's really the core of what we're talking about today. And the answer to that big why is thermodynamics. This is the science that basically lays down the law for energy, heat, and work. For us, it's the rule book that tells us which way change is going to go. So let's dive in. So here's our game plan. We'll kick things off with the main idea, spontaneity. Then we'll get our vocabulary straight with the key terms. After that, we'll open up the chemist's toolkit to look at the equations you'll be using, tie it all together with a summary, and wrap up with a final question to get you thinking.
First up, let's really get a handle on the core concept that explains why things happen in the first place: spontaneity.
So what do we even mean by spontaneous? It's this built-in, natural tendency for a process to happen in one direction all by itself, without any continuous help from the outside. Think of a ball rolling downhill. It just goes. That's spontaneity. That melting ice cube, it's doing the exact same thing, just on a molecular scale. Okay, to really dig into this, we have to be speaking the same language. So let's do a quick run-through of the most important vocabulary. Now, the next couple of slides are pretty packed with key definitions. I'm not going to read every single one, but I really suggest you hit the pause button and get familiar with these. Trust me, it'll make everything that comes next click into place. Here we go, our first set of terms. You'll see some real heavy hitters here. Like entropy, you can think of that as a measure of disorder or randomness. And then there's Gibbs free energy, which you'll see is going to be our #1 tool for predicting if a reaction is a go or a no-go. And here's the second batch. Again, feel free to pause if you need to. Getting these terms down now will really pay off in a few minutes. Okay, now if there's one term from that list that you absolutely have to burn into your memory, it's this one, Gibbs free energy, which we call G. The key takeaway is right there on the slide. If G decreases, the process is spontaneous. It is the ultimate green light for a chemical reaction. All right, now that we've got the concepts and the lingo down, let's see how we can actually calculate this stuff. It's time to open up the chemist's toolkit and check out the key equations of thermodynamics. And here it is, your complete cheat sheet for thermo calculations. Now, I know it might look a little intimidating with all those symbols, but don't worry, we're about to break down a really important part of how you actually talk about these equations, so you'll sound like you know exactly what you're doing. Let's zoom in on this superstar equation right here. This is a big one. It's the link between Gibbs free energy, enthalpy, and entropy. But you're probably looking at it and wondering, what's with that little circle up top on the G, the H, and the S? That little circle means we're talking about standard state conditions, and it has a special pronunciation. You don't say EO or delta G circle. You say not. So E with the circle becomes E naught, and delta G with the circle becomes delta G naught. So let's see it in action in a full equation. You'd read this one out loud as E naught cell is equal to E naught cathode minus E naught anode. It's that simple. And just like that, you know how to say it like a pro. Okay, we've covered the big ideas, the vocabulary, and the tools. Now let's connect all the dots and just nail down the key takeaways from all of this. So, to recap, what makes a process want to happen on its own? It's favored by two things: a decrease in enthalpy, which is like releasing heat, and an increase in entropy, which means more disorder. And here's the really wild part. Every single spontaneous process, from an ice cube melting to a star exploding, increases the total entropy of the entire universe. And this idea is so fundamental, it's enshrined in a couple of laws. The second law of thermodynamics makes it official. The universe is always getting more disordered. The third law gives us a baseline, a kind of ground zero for disorder. It says that at the coldest possible temperature, absolute zero, a perfectly ordered crystal would have exactly zero entropy. And this all brings us back to our MVP, Gibbs free energy. It's the ultimate decider. If the change in G is negative, the process is spontaneous. It goes. If it's positive, it's non-spontaneous. It's not going to happen on its own.
And if it's zero, the system is perfectly balanced in a state of equilibrium. We have flown through a lot of material in this review. So to leave you with something to really think about, here's one final question that takes these ideas to their absolute limit.
We know the second law tells us the universe is constantly, unstoppably moving toward a state of maximum entropy, maximum disorder. So if that's the ultimate spontaneous process, what does that imply about the final state of, well, of everything? What does the end of the universe look like? It's a huge question, I know, but it's one that thermodynamics forces us to ask. Thanks for joining me for this review.